Cephalosporins are considered the second major group of beta-lactam antibiotics to be discovered. The first cephalosporin, which is cephalosporin C, was isolated in the mid-40s from sewer waters on the island of Sardinia. This was based on the observation of an Italian professor who noticed that the water surrounding the sewage outlet was clear of bacteria. Now, similar to Fleming, he presumed that there must be an organism that is producing an antibacterial substance. So he collected samples from that location, grew in lab the microorganisms he collected, and the crude extract of one of those grown microorganisms, which is a fungi that he identified as Cephalosporium acremonium, has antibacterial activity. Later, scientists in Oxford University were able to isolate pure cephalosporin C from that fungus in 1948, but it wasn't until 1961 that the structure of that chemical substance was elucidated. The structure of cephalosporin C has similarities to that of penicillins, in particular isopenicillin N. The side chain is the same, which is derived from aminoadipic acid. As for the bicyclic system, it is composed of a four-membered beta-lactam ring, but this time the beta-lactam ring is fused to a six-membered dihydrothiazine ring. That core structure of cephalosporins is called a cepheme, which is spelled either with a PH or F. The saturated cepheme is called a cepha. Even though penicillins and cephalosporins are slightly different structurally, yet both are derived from the same biosynthetic precursors, which are cysteine, valine, and aminoadipic acid. Cephalosporin C is not a potent antibiotic compared to penicillin G. Its activity كانت تقريبا 1/1000 الactivity of penicillin G, yet it was an interesting compound for two main reasons. It had an antibacterial activity against gram-negative bacteria, same as that against gram-positive bacteria. Another inbuilt advantage of cephalosporin C was its greater resistance to beta-lactamase enzymes. For those reasons, cephalosporin C was considered a very interesting and useful lead compound for the development of more potent, broad-spectrum, and beta-lactamase resistant antibiotics. The optimization of various analogues of cephalosporin C was viewed using the semi-synthetic approach that was used with penicillins, which is simply varying the side chain using, in this case, 7-aminocephalosporanic acid precursor. When having 7-aminocephalosporanic acid in hand, it can be simply reacted with the acyl chloride bearing whatever side chain that is desired. Yet unfortunately, opposite to 6-aminopenicillinic acid, 7-aminocephalosporanic acid was not obtained via fermentation, nor at those times obtained through enzymatic hydrolysis of isolated cephalosporin C. Nowadays, industrially, it can be obtained by using cephalosporin C acylase, a method discovered and developed by Sandoz in 2006. Like prior to that, the only way to generate 7-aminocephalosporanic acid from cephalosporin C was via chemical hydrolysis, which we'll discuss in the next slide. The scheme you see in here represents the method that was used for generating 7-aminocephalosporanic acid from cephalosporin C using chemical reagents. To summarize, the amide is converted into an aminochloride, which is more electrophilic, then reacted with an alcohol to generate an amino ether that is later hydrolyzed. The reason for converting the amide into an aminochloride prior to hydrolysis is based on the fact that if the acyclic amide is to be hydrolyzed directly using acid or base in aqueous media, the more electrophilic beta-lactam will be broken first. Thus, activation of the acyclic amide into a more electrophilic group prior to hydrolysis was necessary. The aminochloride is synthesized using PCl5. This phosphorus pentachloride is an electrophilic reagent. When this reagent is added to cephalosporin C, the most nucleophilic atom would attack the phosphorus. The The most nucleophilic atoms are the carbonyl oxygens, and we have 4 of those in cephalosporin C. The strongest are the carboxylic acid at carbon number 2. It's an ionizable group, which would increase its electron density, thus its nucleophilicity, and the acyclic amide. To avoid competition between these nucleophiles, the carboxylic acid nucleophilicity needs to be diminished. This is done via turning it into a silyl ester, or in other words, protecting it. Now, once this carboxylic acid is protected, when PCl5 is added to the acyclic amide, it will interact with the carbonyl oxygen as shown in this mechanism. The amide carbonyl will attack the phosphorus pentachloride, eliminating a chloride. The chloride will re-attack the carbonyl carbon, eliminating phosphoryl chloride, and the aminochloride is formed. The aminochloride, relative to the acyclic amide and the beta-lactam, is more electrophilic, and this is due to the electron withdrawing effect of the chlorine. Now, direct hydrolysis of the aminochloride in aqueous media will convert it back to the amide. Thus, it's transformed first to the amino ether via reacting it with an alcohol. Then it can be hydrolyzed easily to 7-aminocephalosporanic acid, and this precursor, as we've explained before, is used to generate variant ranges of cephalosporin analogs. Let's discuss now the chemistry of the beta-lactam and cephalosporins. In cephalosporins, the beta-lactam is fused with a 6-membered dihydrothiazine, which is larger than the 5-membered thiazolidine ring in penicillins. Thus, theoretically speaking, the more relaxed 6-membered ring should pose less ring strain on the beta-lactam, and the beta-lactam of cephalosporins should be less reactive. Lacking what is seen experimentally is that beta-lactams of cephalosporins are relatively easily broken and show good activity. This can be explained based on the following observations. The developed charge upon hydrolysis of the beta-lactam will not be localized on the nitrogen, but delocalized due to resonance with the double bond, which stabilizes the resulting product. This explains the fast drop in activity when saturating or isomerizing the double bond, which means that, for instance, moving the double bond to carbons 3 and 4. Now, such isomerization of the double bond will hinder the resonance stabilization of the negative charge on the nitrogen following hydrolysis. The second reason that further enhances the breakage of cephalosporin C and other similar cephalosporins is having an ejectable group, such as a methyl acetoxy at carbon number 3. As you can see in this mechanism, having such an ejectable group means that the developed charge will end up on the acetate, which is a very good leaving group, and the resulting hydrolyzed cephalosporin you see in here is a neutral which is very stable. And an acetoxy is considered a good leaving group because of its relative stability. The negative charge is delocalized via resonance between two highly electronegative atoms. The mechanism that involves elimination of a leaving group is presumed to be either a concerted one, which means that the breakage of the beta-lactam along with the elimination of the acetyl all happen at the same time, or it could be a non-concerted mechanism, meaning that the beta-lactam breaks first, forming a cephalosporic acid, followed by elimination of the leaving group. Another example of a good leaving group that can be introduced to a cephalosporin semisynthetically is methylthiotetrazole, which is found in a number of cephalosporins such as cefotetan. Breakage of the beta-lactam of cefotetan will result in the elimination of methylthiotetrazole. This group can be eliminated because it is similar to acetate, a stable and a good leaving group. And the reason why it is considered a good leaving group is due to the electronegative nature of the atoms constituting it, and most importantly, because of the delocalization of the developed negative charge on sulfur via resonance. What you also need to know about this group is that it has been implicated in clotting difficulties and acute alcohol intolerance. So usually cephalosporins having this group are associated with these side effects. In regards to the mechanism of action of cephalosporins, it is the same as the one we've explained for penicillins. They bind to transpeptidases, and their beta-lactam is broken by the nucleophilic effect of the serine residue in the active site of a transpeptidases. Thus, similar to penicillins, cephalosporins are considered irreversible inhibitors of penicillin-binding proteins. Cephalosporins that have a methylene acetoxy group at carbon number 3 undergoes hydrolysis by the action of esterases. The enzyme breaks the ester, resulting in a carboxylate, which is acetate, and an alcohol. Now, which of those two antibacterials is more potent? Is it the cephalosporin with the methylene acetoxy or the methylene alcohol? You can answer this if you can determine which has a better leaving group. Is it the hydroxyl or the acetate? And I guess you can tell that it's definitely the acetate, since the charge will be delocalized, while in the case of the hydroxyl, it will not be. This means that the alcohol metabolite is less potent. Now that metabolite undergoes spontaneous lactonization. The alcohol attacks the carboxylic acid at carbon number 2, forming a lactone. Now, what about the activity of the resulting lactone? Is it more or less relative to the alcohol? You can answer this if you remember that a free carboxylic acid at that position is necessary for the activity. It is an ionizable group that forms an ionic interaction that is essential for the binding of penicillins and cephalosporins to the active site of their target. So the lactone is not just less potent than the alcohol, it is actually inactive. So in summary, cephalosporins with a methylene acetoxy are not metabolically stable. Acidic aqueous conditions can also hydrolyze the acetoxy, resulting in the alcohol metabolite that will spontaneously lactonize. Recall that the side chain in cephalosporin C can be removed by the action of acylase that is currently used to generate 7-aminocephalosporanic acid precursor. The beta-lactam in cephalosporins, similar to that in penicillins, is sensitive to acids, bases, and beta-lactamases. Hydrolysis in acidic or basic media or by the action of beta-lactamases results in the breakage of the beta-lactam, giving rise to cephalosporic acid. In the case of having an ejectable group at carbon number 3, the products will be a combination of cephalosporic acid and anhydrodisacetyl cephalosporic acid. Let's start now with the structure-activity relationship of cephalosporins, and let us begin with what is crucial for activity. The beta-lactam, the carboxylic acid at carbon 2, and the absolute and relative stereochemistry being cis of carbon 6 and carbon 7 are all essential for activity. Similar to penicillins, the side chain on carbon 7 affects antibacterial activity and resistance to beta-lactamases. Yet there are two other positions that can tolerate change without diminishing or affecting negatively the antibacterial activity of cephalosporins, and these are the substituents at position 3 that mostly affects chemical and metabolic stability, and position 7 that we'll elaborate more about on the next slide. In this slide, we'll be considering the details of allowed substitutions on positions 3 and 7 and how they affect activity of cephalosporins. As I've mentioned earlier, the nature of the substituent on carbon 3 affects mostly the metabolic and chemical stability. The effect on antibacterial activity is seen with heterocycles, where generally speaking, the 5-membered heterocycles show improved activity compared to 6-membered heterocycles. The sulfur at position 5 can be replaced with an oxygen. This leads to enhancing stability toward beta-lactamases, yet it lowers the antibacterial activity. The proton at position 7, based on cefamycin that was isolated later, can be replaced with an alkoxy, in particular a methoxy. that has been found to increase the antibacterial activity and stability against beta-lactamases. As for the amide side chain, having an amine increases the oral stability similar to penicillins, lakin it's actually the nature of the substituent on carbon 3 not being an ejectable group is actually the detrimental factor in the acid stability of cephalosporins. What greatly enhanced cephalosporins' stability towards beta-lactamases is having a substituted oxime or alkene on the alpha carbon, as you can see in these examples. A double bond, as you all know, cannot rotate, which means that if atoms of any double bond have one or no protons, this means that there will be two possible stereoisomers, which are Z and E. As in the case of biological activities of all stereoisomers, one usually shows better activity versus the others. In our case, Z-oximes or Z-alkenes are almost 100 times more resistant to beta-lactamases than the E stereoisomer. Production of beta-lactamases, similar to penicillins, constitutes the major route of resistance against cephalosporins. Although many strains of bacteria constitutively produce beta-lactamases, yet in other strains the production is induced. As we'll see later, some cephalosporins, for instance cephamycins, induces upon destruction of the peptidoglycan the genes responsible for beta-lactamase production.